Hi everyone, I'm Jiale. Really appreciate your time. I'm excited to share our work on BingoGCN. It's about accelerating large-scale GNNs efficiently using partition and a strong lottery ticket. Graph convolution neural network are powerful for handling irregular graph data. It supports various tasks like node classification, link prediction, and even graph classification. However, achieving real-time large-scale GNN inference still poses significant challenges, which our research aims to solve. As GNN scale to large graphs, aggregation becomes a memory-bound bottleneck. The diagram shows a node V collecting its neighbors from node A to D. In hardware, this translates to multiple random DRAM accesses, since each neighbor might reside in a different memory location. And this is just for one node. For billions of nodes in web-scale graphs, this access pattern results in poor DRAM efficiency. Some accelerators adopt a scalar-based approach, which features are first read and then distributed via a crossbar to multiple accumulators. After finished accumulation, the destination nodes finally will be stored in the DRAM. As the graph scales up, the on-chip buffer can no longer store all destination nodes. Consequently, many features must be repeatedly fetched from and written to the off-chip memory. This naive approach became highly inefficient, especially when a large number of neighbors require updates. Overall, large-scale graph introduce significant communication overhead due to increased node and edge counts. Previous studies like SOTA, accelerator flow GNN, assume the entire graph can fit in the on-chip buffer, which only works for small graphs. However, this assumption doesn't hold for large-scale graphs, making such design unscalable. Graph partition offers a promising solution to tackle memory and communication bottlenecks. Using tools like Metis, we can divide a large graph into smaller subgraphs to enhance locality and reduce it per partition buffer size. However, this approach comes with a trade-off, because we cannot ignore interpartition edges. Excluding them would severely degrade GNN accuracy. As shown in this picture, increasing the number of partitions leads to an increase in interpartition edges. These cross-partition links highlighted in blue, cause frequent and irregular memory access, especially to off-chip DRAM, which harms efficiency and scalability. To address these communication challenges in GNN, we propose a cross-partition message quantization method named CMQ. It quantizes 4 precision messages across different partitions and reduces memory communication cost. The optimized model can still achieve competitive accuracy while reducing the memory cost. And each partitioned heat map looks like a bingo card here, right? So that's why we call this BingoGCN. Traditional quantization compresses values one by one, offering limited reduction. In contrast, vector quantization maps entire vector to centroids in a high-dimension space, capturing features and enabling much higher compressibility. We further apply this idea to cross-partition message quantization, or CMQ, where inter-partition messages are replaced by centroid indices from a codebook, significantly cutting communication cost. Now let's move into details about how to implement vector quantization to the graph. Let me give an example here. We've divided the graph into 3 parts. For the middle part, it has interconnection between others, and they are usually stored on the off-chip memory. We utilize an on-chip buffer as a codebook. It stores quantization values of all cross-partition nodes, and we find all cross-partition nodes can be mapped with the corresponding centroids, like here C1 and C2. Then we replace them. Following this style, we can finish from P1 to P2 to P3, and compared with the traditional method, this can significantly illuminate the off-chip memory access of interpartition nodes. At the end of each GNN layer, node features are updated and need to be reflected in the quantization codebook. We propose an online and hierarchical update scheme. As shown here, each node first compares against the level 1 centroids to select a cluster. Then, search within the selected L2 centroids to find the closest one. Once assigned, it updates both L1 and L2 centroids using a moving average manner. And this short animation shows how two nodes came in and updates both L1 and L2 centroids. Okay, let's look at another challenge. GNN are also computation bound, especially in XW step. In this stage, each node features are multiplied by a weight matrix. To address this, the strong lottery ticket offers an exciting opportunity. It demonstrates that a neural network contains a subnetwork that can match the original models. Here we use a learnable supermask to select a sparse subnetwork. Moreover, instead of training the weights, all weights are randomly generated without any fine-tuning. It's amazing, right? This leads to a large potential benefits for hardware design since we don't need to access them from DRAM, we can generate them on the fly. However, applying strong lottery ticket to GNN brings two main issues. First, it often uses unstructured pruning, which creates irregular weight patterns that are difficult for hardware to handle. And structured pruning helps us, but it hurts accuracy, right? Second, current strong lottery ticket acceleration like HiddenNet use random number generator, but it usually generates dense weights and it's not aware of sparsity. This leads to generating many unnecessary weights, lowering P utilization. To address these computation challenges in GNN, we adopt a structured form of strong lottery ticket that is better suitable for hardware while still maintaining competitive accuracy. Each lottery ticket corresponds to a sparse, efficient subnetwork, and each partitioned heap map looks like a bingo card. So, the whole meaning of the bingo is combining the best of strong lottery ticket and partition for efficient GNN acceleration. We integrate strong lottery ticket into GNN via fine-grained structure pruning, keeping a fixed number of non-zero per block, while allowing flexible positions. This strikes a balance between sparsity and accuracy. We also adopt a SOTA approach of reconstructing weights on the fly using random number generator, RNG, but enhance it with a seed, tied it only to valid indices. Since weights are only binary, like positive, negative, 1, and 0, computation becomes multiplierless, using only additional and bit flip. CSR indices guides the valid selection, simplifies the hardware, and reducing the energy cost. Finally, we design a dedicated engine for online CMQ and SLT processing, enabling efficient GNN computation. To efficiently support the combination stage in GNN, BingoGCN leverage the high sparsity in both the input and the weights, reducing up to 98% and 80% respectively. We adopt a CSR-based sparse representation, row-wise tiling, and systematic array-friendly mapping strategy. This design reduces redundant computation and enables efficient processing of sparse-dense matrix multiplication. To handle this sparse aggregation step, BingoGCN first converts the agency matrix into an age list for extremely friendly accesses. Each age is processed by the scatter unit, which supports message passing and age-level embedding integration. And finally, the CMQ unit updates corresponding codebooks in real time, enabling efficient output generation with more than 99.98% sparsity. Here is the overview of our BingoGCN hardware, which tightly follows the algorithm proposed. Query and replacement. We first use the CMQ unit to map incoming nodes ID to codebooks. Secondly, message passing with SLT. We perform message passing using fine-grained structure pruning. Age-aware aggregation, we support age embedding, which can combine with features and scatter to the destination nodes. And finally, online CMQ update. We update the codebooks use a hierarchical online update. All models are connected through a main control and shared object memory supporting GCN inference. So for intranode, blue arrows illustrate that it begins from object memory with nodes and then goes with combination engine and aggregation engine, finally stored in the object memory. For the internodes, orange arrows illustrate that it begins from CMQ ping-pong buffer and also goes with combination engine and aggregation engine, then use CMQ system to update the codebook. So here's our evaluation step. We use 3 and 4 layer GCN and evaluate on both node level, graph level tasks. Our metrics include accuracy and latency speedup. For baseline, we compare against a SOTA hardware accelerator like GNN and both CPU and GPU. And we use algorithm level baselines such as dense training model and unstructured strong lottery ticket pruning and random sampling. So this figure shows the performance of fine-grained structure pruning under our SLT framework. As you can see, there are different sparsity levels, and on datasets like Cora, OGB, and Mobase, our method achieves comparable accuracy to dense weight learning, even at 80% sparsity. This demonstrates that fine-grained structure pruning preserves performance while enabling high compression and efficiency. Here, we also compare CMQ with random sampling. And here CMQ is blue line, consistently delivers high accuracy, especially at very, very low sampling ratios. On OGB and archive, random sampling drops accuracy by over 4%, while our proposed method limited to just 0.5%. This shows CMQ achieves better message approximation error with minimal accuracy loss. We just saw CMQ outperforms random sampling at low sampling ratio. Now, under extreme partitioning, like we divide it into 512 parts, what will happen? We're removing border nodes will cause massive accuracy drop, over 50%. But our CMQ keeps the drop to just 2.7% by effectively approximating the interpart messages. We compare BingoGCN with a GPU implementation and the previous SOTA accelerator flow GNN. Compared with GPU, BingoGCN achieves up to more than 7 speedup and up to 40 times energy efficiency improvement, thanks to our lightweight structure, strong lottery ticket, and data flow aware hardware. Against with flow GNN, BingoGCN achieves more than 2 to over 65 times speedup and up to 12 better than energy efficiency. So to summarize, we tackled the key challenge in large-scale GNN inference, especially the memory, communication, and buffer overhead caused by irregular data accesses. We proposed the BingoGCN framework, which introduced cross-partition message quantization to reduce the cost of inter-partition communication. On the compute side, we applied strong lottery ticket with fine-grained structure pruning, allowing us to significantly shrink the model size and run with multiplayer-less sparse hardware. Together, these techniques enable scalable and efficient GNN acceleration with less memory, less compute, and the same competitive accuracy. This is the whole presentation. Thanks for listening. Any questions?